We will continue our discussion of circular motion. Let me start by writing the position vector. Well, in general, whether circular motion or any other kind of motion, in 2 dimensions, the position is given by the 2 coordinates. And I write it as a vector, like this. Now, in the case of circular motion, as long as your particle is on this circle, it is easy to see the relation between its x coordinate and the radius of the circle and the angle theta. What is x? It's just r times cos theta, right? And what's y? Y is this, the y coordinate of this point. It is just this length r times sine theta, right? But for circular motion, the length r from the center of the circle is constant. So I can factor it out, and it is not a function of time. What is changing in the motion is only theta. So x is r times cos theta of time, because the angle is changing as time goes on. Okay? Plus the y coordinate has a sine in it. Okay? Now I want to find the velocity. The velocity is a vector. The x component of the velocity is, of course, just the velocity in the x direction, the rate of change, dx dt. And let me write it one more step. So the velocity is the derivative, the change of position. The position is a vector and it's changing. It means both of its components are changing. So the v vector, the velocity vector, is the derivative, time rate of change of the position vector. And the x component of velocity is dx dt, and the y component of velocity is dy dt. Okay? This is clear. Now let me start taking the derivatives. Well, dx dt, here is x, r cos theta. R is a constant, so I just write it down. But I have d cos theta dt plus, again r is a constant. I can leave that constant outside the parenthesis. Okay, and I have here d sine theta dt. Okay, is this clear so far? So what do I see here? This particle is moving along a circle. This means its distance from the origin, r, the radius of the circle, is a constant. So what is changing as time goes on? It's just the angle. As the angle changes, its cosine changes, so the x position changes, obviously. As I move around, both my x position and my y position is changing. And the reason it's changing, the coordinates are changing, is only because the angle is changing. The distance from the origin doesn't change. Okay? If this was not a circle but something else, then r would also be changing as well as theta. But here, it's easy circular motion. R is fixed, theta is changing. Okay, so now I have a problem. Some of you may have learned it before or may remember it, but I will assume that we don't know how to take the derivative of sine and cosine. Okay? And we learned that now. But let's first look at this. What's happening here is as time changes, as time goes on, the angle changes. And as the angle changes, its cosine changes. Okay? So here we have an example of what we learned some lectures ago about taking derivative of something which depends on something else. So how would I take the derivative of cos theta with respect to time? Well, the rule is simple. It's called the chain rule. You will remember from your homeworks. Okay? You do it like this. What have I done? Well, d cos theta dt, I remember, is really a division. A division of some small numbers, but it's a division. So if I divide and multiply by the same number, okay, I'm just multiplying by 1. And I choose the number that I divide with and multiply with as d theta. So d theta over d theta is 1. I multiply this by d theta over d theta. And then I have d cos theta divided by d theta times d theta divided by dt. So I'm just repeating my earlier argument that if you have something that depends on something else, the net derivative is done in steps, d cos theta, d theta. What does that mean physically? It means how is the cosine change as the angle changes? Why does the angle change? I don't know yet. Okay. How is the cosine changes with respect to the angle? That's d cos theta, d theta. And then the angle is changing. Why is it changing? Well, it changes with time. It's changing due to motion. So there's another change in the problem, and that's the change of the angle with respect to time. I multiply these two things, and I get the net change of d cos theta with respect to time. Okay? That's understood, right? Now, let's remember what we learned last time. When we have uniform circular motion, theta, the angle, increases with time at a constant rate that we called omega. So there is one part of this formula that you can calculate. Now you tell me, what is d theta dt? Does anybody understand the question? Theta equals omega times t. Omega is a constant. Okay. What is d theta dt? Just omega, right? So one part of this calculation is easy. The d theta dt part, that's just omega. That leaves me with the problem of figuring out how does the cosine of any angle theta, in general, it doesn't have to be omega t. If you change an angle by a small bit, what happens to its cosine? Okay? Now let us derive this formula. Okay? I'm not going to take it out of my pocket, give you a formula to memorize. We are posing the question, if theta changes, how does its cosine change? Now to understand this, let's make a picture. So here's my picture. Let me draw a part of the circle. Here is x, here is y. This is theta. Okay? And let me choose this length, the radius of my circle, r equals 1. Why? To make life easy. Okay? So I don't have any r's around. R is not relevant. This means this length here is 1, and this length here is just cos theta. Clear? Now let me change theta. Let's say theta increases by a small amount, delta theta. Let me draw that in a different color. So this is delta theta. And this whole amount is, the purple one is, this angle is theta plus delta theta. Okay? So the value of this point is cos theta. And the value of this point is what? Let's look at this figure now. I want you to follow this step by step very slowly and really understand all the steps. You can all get it. Okay. Now I have this triangle. This side was 1. And so this length here is cos theta. All right? Now I have a new triangle, this one, whose angle is increased by a small amount delta theta. So this is theta plus delta theta. And this length here up to this purple point is how much? Cosine of theta plus delta theta. Does everybody get this? For each triangle, the x leg is just the cosine of that angle. So that means if I draw a circle with radius 1, for any angle theta, I can just take my ruler on the x-axis and read off numerically the value of cos theta from the axis. It's an analog computer for calculating cos theta. Okay? So let me write this in purple. This new point is cos theta plus delta theta. Now, in taking a derivative, what do I want? I want to see how this cosine, this length along the x-axis, changes as theta changes. First, answer this question. I have increased the angle theta to theta plus delta theta. Does the cosine become larger or smaller? Smaller. Cos of theta plus delta theta here is shorter than the cos of theta. Is this clear? Now what do I want? Of course I want to calculate from this figure the following. I want to know cos of theta plus delta theta minus cos of theta. This is what I need in calculating derivative. How much has this cosine changed? All right? Now, can I see that in the picture? Yes. It is this length. Right? So let me also write that down. The change in cosine theta is the new value of cos theta, which is cos of theta plus delta theta, minus the old value of cos theta. Okay? And geometrically, in this picture, I can read off the numerical value of this by just measuring the green segment here. Is this clear to everyone? Okay. Now the trick starts. Now I will do some drawings geometrically to figure out how much that length is in terms of theta and so on. Okay? I won't write many symbols just to keep the picture simple, so I'm using color code. So the green line equals the other green line. Yes? I complete this triangle here. This length is approximately equal to delta theta. Why? First, this green sided, green and purple little triangle here, this side is a straight line, but when the angle is very small, which it is, okay, when delta theta is very small, the length of this straight green line is approximately the same as the length of the arc in black. The length of arc on a circle is equal to the radius of the circle times the angle at the center provided the angle is in radians. Okay, that was definition of radian. Now my circle has a radius of 1, so the length in meters of this little black arc facing delta theta is just delta theta. That means if you really take a little string or rubber tape meter, put it there and read off in centimeters or meters, you will read the value of the angle in radians. Is this clear? This is a tricky point, so maybe some of you didn't understand, and I will explain it again. Does everybody get it? Right? If the angle is small, straight line almost equals the circle piece, and that piece is just the radius times the angle in radians. The radius is 1, so this length is delta theta. Maybe it is 0.0125 radians. You can read it off with your tape meter. Yes? Okay. Now I have this angle here. I have this angle, let me call it theta prime. What is that angle? Well, first, what am I going to use it for? I know that delta cos theta is this green length here is simply this length here times sine theta prime. Let me write that down and then we'll discuss it. Why is that? Well, because this is a little triangle with a right angle here. This length is about equal to delta theta times sine of this angle gives me this length. Is this clear? Now, does anybody have any questions? On to the next step. I want to know what is this angle theta prime. I have this angle theta here. Well, this is also theta. This is theta. And now look at this triangle here. When this angle becomes very small, this green line here becomes almost on top of the circle. It becomes tangent to the circle. So this full angle here becomes a right angle, 90 degrees, pi over 2, okay? This means if this is theta, this is 90 minus theta, and this is also theta. Does everybody see that? Okay? Any questions here? If you have a question, please ask, because I don't think you understand immediately. You will understand, but does everybody really understand this last step? Any questions? Is it okay? Okay. So let me just note this argument here. Right angle means dik açı. Okay. So we have theta prime equals theta. Okay? So we have here so what have we done? Let me repeat. We have made this drawing, this picture, and we have realized that when I take the derivative, I want to calculate how much cos theta has changed, and that is just measuring this length. This length equals this length, this length equals this side times sine of theta prime, this side equals delta theta, theta prime is equal to theta. So I have got the result that the change in cos theta is delta theta times sine theta, except I have a minus sign here because as I realized at the beginning, this is smaller. Cos theta plus delta theta is smaller than cos theta. So I have minus delta theta sine theta. That is the change in cosine theta when I increase theta by a small angle delta theta. Is this clear to everyone? Now I am ready to calculate the derivative. Remember, what I want is to calculate the derivative d cos theta d theta. What is that? It's the limit as delta theta goes to 0 of cos theta plus delta theta minus cos theta divided by delta theta. The change in cos theta divided by the change in theta, and then I want to have this exact value, so I want to make delta theta smaller and smaller and smaller. So I take the limit, okay? And as usual, before I take the limit, I need to figure out how the expression here depends on delta theta, and I've just done that. So let me put that in place. It's minus sine theta delta theta divided by delta theta. I still have to take the limit. But again, as usual, when I have a small number downstairs, I also have a small number upstairs, and I have now figured out how small that is, and the delta theta cancelled. Clear? So we have learned by making this drawing and using geometry as an analog computer, okay, we have shown that the derivative of cos theta with respect to theta is just minus sine theta. Clear? Any questions on this?
Why is it minus?
Okay, why is it minus? I am calculating this expression, cosine theta plus delta theta minus cosine theta. Cosine theta plus delta theta is the length of this purple line, or the distance of this point from the origin. Cos theta is this. Which is bigger? Cos theta. So this quantity must be negative. Its absolute value, the number, is equal to this line. Okay, but I'm subtracting this from this, so after I calculate the length of the line, I put a minus sign in front. Okay? Now, in the same way, by looking at the same picture, I can calculate the derivative of sine theta. I will not do it. I will leave it to you as homework to really understand this. You will use the same picture, but this time, okay, this is sine theta, so you will draw it here. This is sine theta, this is sine of theta plus delta theta, and this is the difference. And now you want to calculate the length of this line. You get to your small triangle again, and you will figure it out. Okay? But please do it. Especially if you don't understand the details of what I have just done, try to do it yourself or sit down with a friend after class and go through this. Because if you do this, you will really understand how logic works and geometry works in mathematics. And this is about as complicated a mathematical derivation as we will do in this class. So right at the beginning, if you go through the sine argument, first yourself, and then if you can't do it, go over it with a friend, then you will get it straight. And this is as much mathematical thinking as you will need in this course, so then you will be free. Okay? Of your fears, if you have any fears. Okay? So it's an important homework. Find d sine theta, d theta. Okay? Any questions? Now let's take a break for 10 minutes.